Alright, good morning class. We're going to get started with this lecture today. Last lecture we covered this section 3.4, which focused on k-values and on flash calculations. We didn't get a chance to do the problems, so today we're going to do the problems. And then what we're going to do is do some general practice problems on this unit, because next week you have a tutorial and a quiz. So I decided that I'll delay the start of the next unit till after the tutorial and the quizzes. So just to quickly highlight from what we did the last class, we introduced the k-value, which is the ratio between the mole fractions in the gas phase divided by mole fractions in the liquid phase. If Raoult's law applies, then that means the k-value can be obtained using the saturated pressure divided by total pressure. And if it's modified Raoult's law, then you also have to have the activity coefficient included in that as well. Then skipping over, so I'm going to skip over the charts because we covered that. Skip over all the way to where we derived the expressions for flash calculations. And we got this equation here in the end. So what we were saying here is that if we have a composition and we know our feed composition, so that would be Z. And we know the temperature and pressure of our system, so we can obtain the k values, whether from the charts or if I apply Raoult's law and I know the saturation pressures, that I can find also the k's that way. And then what we would do is iterate this, assuming an initial guess for the vapor, and then calculate all this, check what it equals. If it equals 1, then we have what we were looking for. If it doesn't equal 1, then we need to guess another v, and then repeat that until we get this equation equal to 1. Once we have that, then we know we have the vapor, and we also know that we can get the mole fractions in the vapor phase, which is basically this equation separated into its separate terms, right? Which is, for component 1, y1 equals z1 k1 over 1 plus k1 minus 1 v, and v would be something that you already figured out. Once you do all that, then you can get the mole fraction in the liquid phase by applying this expression, which takes the k that you already have, right, and uses it in the calculation of x. Because you already know y, k we already know from the first step, so then we just apply it and find x. So today we're going to practice that in this problem, example 10.5. So I'm going to move to drawboard here and start writing. Alright, so in this system, we have 3 components. We have acetone, acetonitrile, and nitromethane. Temperature is given 80 degrees Celsius, and the pressure is 110 kilopascals. The overall composition, meaning liquid with vapor, if it was 2-phase, or if it was all 1-phase, it doesn't matter. The overall composition is 0.45 component 1, 0.35 component 2, and 0.2 component 3. In this case, it's saying assume that Raoult's law is appropriate to this system. When you hear that, it means k can equal p sat over p. All right? Determine L, V, Xi, and Yi. The pressures of the pure species at 80 degrees Celsius is given here. If the pressures weren't given, then you know you can use Antoine's equations to find them. Given a certain temperature, you would calculate it and find it and use it. Alright, so first thing, as I mentioned, assume Raoult's law. So we can say assume Ki equals to Pi sat over P. In this case, we have the pressure, right? And we have the saturation pressures as well. So from those, I can find K for each component in the system. So my goal is to find, in this case, L, V, and the compositions, right? So the first thing I want to check is this in fact a 2-phase system, or is it a single-phase system? What value would help me find that? So if we look back at the plots, right, we have pressure versus xy, right? This is at constant temperature. Let's say this is at 80 degrees Celsius. And then I have my, what are these lines? Bubble line, dew line. Up here I'm all liquid, down here I'm all vapor. So I need to check where am I on this, right? If I'm in here, it's two-phase. If I'm in here, all liquid. If I'm in here, all vapor. So what values can I calculate to tell me where am I on this? So we already know the compositions here. And in this case, it's a three-component system. So this diagram does not apply. This is for binary system only. Okay, but in general, for understanding, you can use it as a reference. Okay, so if I want to know, do I have two phases or one phase? What on this can I use to know that? So what would that give me? So it's a mixture, right? So the behavior of a mixture is different than a pure substance. Okay? So that's one idea. That would work if it was a pure substance, it would work. But for a mixture, the behavior is different. So we can't take that same rule and apply it here. So you were saying?
Multiply the composition by total pressure, it's equal to that.
Look, it's very simple. Basically what you need to know, at this given temperature and this composition, what is my bubble pressure and what is my dew pressure? If I know these two pressures, any pressure in between means it's a mixture. Alright? So that's the goal. So we're going to try to find what is my bubble pressure and what's my dew pressure. So we apply the general equations that we derived before. In this case, Raoult's law applies, so we apply it with the same ones that we did before Raoult's law. So step one, we want to find the bubble pressure. So check bubble pressure. And we said it's Raoult's law, so YIP equals XI PI sat. If you remember, for bubble pressure, we're going to assume we're in what phase? We're liquid and we're starting to vaporize. So then we're going to assume these compositions here are all compositions in the X, in the liquid phase. And then, so we would know all the X's, but we wouldn't know the Y's. So to find the pressure there, we would isolate the Y, do the summation, and get the... So basically what we're going to get is P equals the sum of everything that we see here. And that would be the bubble pressure. Remember, the sum of YIP is equal to P sum of YI. Sum of YI's is 1, then it disappears. All right. So we're going to just write it, P bubble pressure, or P bubble, equals the summation. In this case, we have three terms. So we're going to have I equals 1 to 3, and XI, PI sat. PI sats are all given, right? And we're going to assume the composition is all in the liquid, so we'll have all that as well. So we get X1, P1 sat, plus X2, P2 sat, plus X3, P3 sat. You plug in the values, okay? 0.45 times 195.75 kilopascal, okay, and so on. You just plug in the values, okay? Then we're going to get bubble pressure is 132.4 kilopascals. So, is our pressure higher or lower than this? It's lower, right? So that means at least I know I'm not a liquid. So now I'm at the phase, I'm not a liquid. Either I'm a vapor or I'm a mixture of the two. So we need to find what is the dew pressure. So this is greater than P, therefore not liquid. Dew pressure. So step 2, check dew pressure. And in this case, the dew pressure again derived from this expression where we isolate the x and we get it to equal 1, and that is equal to P2 summation I equals 1 to 3 1 over yi pi sat is the expression. So again, you plug in the values. Okay, I'm not going to do that. In this case, we're assuming the y's are z is equal to y, or y equal to z. So whatever composition we have up here is all in the vapor phase, and I'm just starting to condense. So that's the dew pressure. So you do you plug in the numbers, you get 101.52 kilopascals. My pressure is 110. So that means this pressure is lower. Therefore, we know we have a mixture. So we have liquid vapor mixture. So this is less than P, therefore we have liquid vapor mixture. So now we're going to go to evaluate what the K values are, because I'm going to need them. Where am I going to need them? I'm going to need them in the equation that I showed in the slides, right? I'll just write it down here. So the summation from I equals 1 to 3 for Zi K divided by 1 plus Ki minus 1 times V. This summation should equal to 1, where this would be summation of my y's. Why? Because each one of these would be a y. This is derived for the flash calculations. So the goal here in this problem is to find what's the amount of liquid do I have, what's the amount of volume or vapor, and then the compositions of those. So we're going to assume 1 mole and work with that. Why? Because this expression here assumes 1 mole, right? L plus V equals 1, and that was what was used to derive this expression. If your system has more than 1 mole, you could solve it using 1 mole first, and then that will be your fraction. Then you multiply by the total number of moles, and then you can find how much is actually there. All right, so to use this expression, I already have the z's, right? So z's are known, they're given in the problem. I don't know the k's yet because I didn't calculate it yet, but we said because Raoult's law applies, then I can calculate it using pi sat over p for every component. So we're going to do that. And once we know that, then we're going to have to do trial and error to figure out what is the vapor that will give the summation equal 1. All right, so let's do that here. So we're going to calculate the K values. So Ki equals pi sat over P, and then that means for K1 it's going to be 195.75 kilopascals divided by 110. That gives you 1.7795. So do the same thing for the other two components. You're going to get K2 is 0.8895 and K3 is 0.4575. So we know our case. Now we move on to try to solve for vapor. So for the vapor, I did this all in Excel, okay, but you could do the same thing on paper, okay? If you get this in an exam or a quiz, what we're going to ask potentially is you do 2 iterations, okay, and then that's all you need to do. So if I open up here my Excel file where I solved this, all right, so this is example 10.5, and if you see here, this is my composition, Z1, Z2, Z3, right? It should be the same as what we see here, right? 0.45, 0.35, 0.2, all right? These are all the K values we calculated, all right, using pi sat over P. And then what I'm going to do is take an initial guess for V. What I did here is I split this into 3 different terms, okay, which we have 3 components. So the sum would be adding this 3 times, 1 for every component, which should equal 1, right? So the first guess, I guess 0.7 moles of vapor. I did the math, I did the sum, I got 1.003. I took another guess, 0.9, did the math, I got 0.99. To do linear interpolation, it's important, okay, that you cover that 1. So 1 should be below, 1 should be above. Because if you try to interpolate and it's not, the 1 is not in between, it's extrapolation and it'll throw you off, basically. So it might affect the iterations that you do. So in this case, I did linear interpolation. So to find where the 1 would be. So if I double click here, and in Excel you can use this function called forecast.linear. Okay, where the first value is the 1, that's my goal. I want to get the 1. And then you give it, it's the y values, and you give it the x values. Okay, so the x values is what we see here. The y values is what we see here. So it does the math for me. So the guess is 0.776. I take the terms, I plug it in here, I do all the calculations, I add them up, it doesn't equal to 1. Again, you can continue, okay, until you get exactly 1, or approximately almost 1. You can use solver. This is solver right here. I mean, one way to guess is if your pressure is closer to one of the bubble pressure or the dew pressure, then you would know which one is more dominant, right? So if you're closer to your dew pressure, that means I have more vapor. If you're closer to the bubble pressure, you have more liquid. So that's one way of gauging, maybe, what's my initial guess.
This is for the vapor?
This is vapor. Yeah. All right. So that's how you do it. You do all the math. You find that V is equal to, in this case, 0.7365. Okay. So we can just write that down in here. Using iterations. And what I can do is upload this Excel file so you guys have access to these calculations, and then you could do it on paper as a reference. So using iterations, the amount of vapor that we have is 0.7365. Actually, I wrote 4 here, so I'm just going to go with the 4, just because the rest of the calculations have the 4. But it's the 4th decimal place, okay? Doesn't affect the results that much. All right, so now we know the vapor. From there, I can take this expression and use the vapor in there for one component. So now I would put, instead of Zi, like we put Z1 and K1 and so on. And that way we can figure out what is the mole fraction in the vapor phase for component 1. Then we do the same for component 2 and then component 3. So you'd have to do it, because it's a 3-component system, you have to do it at least for 2 of them. And then the third one you can do 1 minus, y1, y2. So here, I'm just going to write down, so determine the composition in the vapor phase, which is the yi's. And in this case, y1 is going to equal to z1 k1 over 1 plus k1 minus 1 v. We already solved for v. We plug in the values. I'll just do the first one here. So 0.45, 1.7795 divided by 1 plus 1.7795 again minus 1 times v, which is 0.7364. All right. Do the math, you're going to get 0.5087. Do the same thing for y2, you get 0.3384, and then y3, 0.1524. Then to find the mole fraction in the liquid phase, right? What do? We use the k's, right? So k is yi over xi. I know the k's, I know the y's, so then I just multiply, or I divide y by k, I get x. So xi equals yi over ki. So you simply just do the math there. So x1 equals y1 over k1. y1 is 0.5087. k1 is 1.7795. 0.2859. So same thing for x2. You get 0.3810. And x3 is 0.331. Now with respect to, so the question wanted the compositions, wanted how much vapor I have, but it also said how much liquid I have. So how much liquid do we have? Right. So we just do for liquid, it's going to be 1 minus V. Okay, I actually didn't do that math, but it's going to be 0.27 or something. Okay? All right. So that is this question. So let's go back to the slides here. Go to the next question. Question 10.6. So here it's asking, for the system described in example 10.4, what fraction of the system is vapor when the pressure is 200 psi? And what are the compositions of the equilibrium, vapor, and liquid phases? So if we go back to example 10.4, okay, we find that the dew pressure and the bubble pressures are 126 and 385. The pressure here, 200, is between those two values. So that means I have liquid vapor mixture. Now with respect to the composition, that was something given in the problem. So that problem had 3 species. It had methane, ethane, and propane. So 10% methane, 20% ethane, 70% propane. For this problem, what we would do is have to go to the table, the charts with the K values, because we're not assuming Raoult's law here. And we go to the table, which is basically this chart here. And if you remember, we have to find where methane is, where ethane is, and when propane is. We draw a line from the temperature of the system, in this case it's 50 Fahrenheit, and the pressure in this case is 200. So we draw a straight line. Wherever it intercepts with those lines will be my K values. So approximately methane is 10, ethane 1.76, propane 0.52. So that's what we see here. 10, 1.76, 0.52. So that's the K values. Now, to figure out, how much vapor do we have? What's the fraction of the system, or what fraction of the system is vapor? Same problem that we just did, right? We guess an amount in the vapor phase, and then do the math. In this case, the math will be checking whether the sum of the y's, again, is equal to 1 or not. Same thing as before. So first guess, 0.35. You do the math using the expressions that we have. So you do the sum of the y's, you get 0.957. Is it 1? It's not. Take another guess, 1.018. Interpolate, find the value, till you get to 1. Okay, so same as what we just did. Same equations, all right? And then from there, if you wanted more information about what's the compositions, just like we did in the example, you can do the same thing. All right, so I'm not gonna, we already covered all this work in the previous example. So for practice, you can practice this at home, okay, using this example. So what I'm gonna do now is I'm gonna go through some other general kind of problems to make sure your understanding of the material for the unit, parts of the unit is there, so that for next week we have a tutorial and quiz, so you're somewhat prepared for those. Okay, so I'm delaying the start of the next unit till after the quiz and the tutorial. All right, so I did upload this document. Okay, so I called it practice problems. And it's got a set of problems, as you can see here. The first one has multiple parts, and then there's a second and third problem after that. All right, so the first problem, use the following PXY diagram for ethanol and ethyl acetate at 70 degrees. So this whole thing here is at 70 degrees already. To answer the following question, does this mixture system or slash system exhibit an isotrope? If yes, what is the composition of the isotrope? Should be straightforward. Do we have an isotrope?
Yes.
Yes. So in this case, the answer would be yes. And the second part says, what is the composition of the isotrope? Right, so we take this point and we go down
0.43.
and we get whatever is on the x-axis there would be my first component. All right, so approximately, in this case, it's around 0.44 or 0.43. I mean, can't really tell. So just approximately x1 equals to y1, and they're approximately 0.44. And then for x2, y2, they're also equal to each other, and they're approximately 0.56. So 1 minus what we see there. Okay, and in case they were asking what's the pressure, at that point, you just read what's on the y-axis. Okay, so the pressure would be P equals 92 kilopascals. All right, straightforward. Next question. What is the vapor pressure of ethyl acetate at 70 degrees Celsius? So from the previous question, ethanol was 1, ethyl acetate was 2. What is the vapor pressure of pure ethyl acetate at 70 degrees Celsius?
X2, right?
Mm-hmm.
So I go to
0 or 1?
0.56, and then it's 1.
So here on the plot, we plot the more volatile, which is typically component 1. Ethyl acetate is component 2. That means if I have 0 of 1, I have 1 of 2. So to know what's the vapor pressure for ethyl acetate at 70 degrees, right? That's a PSAP, you can say, for ethyl acetate. So that would be whatever we read here. Okay? So in this case, x2 equals 1, meaning x1 equals 0, and P2 SAT equals 80 kilopascals. Okay? Should be straightforward. Consider an ethanol-ethyl acetate, again, mixture. X1 is 0.2, 70 degrees Celsius, and 86 kilopascals. What are the compositions of the liquid and vapor phases? Right, so here we go to 0.2. Then we're going to move up to where? To 86, right? So 86 is here. So we're going to go to 86, which is right here. So what do we have? What are the compositions of the liquid and the vapor phase?
The other one?
Hmm?
The other,
Which other one?
the other line, black line.
This black line?
Sorry.
This one?
Yes.
Yeah. Okay, look. Did we reach the point that's past the due pressure? We didn't. You need to go all the way up to this pressure for you to have a mixture. So at this pressure, we're still all vapor. Up here is liquid, this is vapor, in between liquid vapor. So in this case, it's all vapor. And the composition would be the same as what is given. Then you would draw the timeline. There's another example on that. Okay? So part C, we said x1 is 0.2, so we get y1 equals to 0.2, same thing, and y2 equals 0.8, and all vapor, no liquid. Next problem. Consider an ethanol, ethyl acetate, again, same thing. This case, x1 is 0.8, temperature is 70, pressure 84. What are the compositions of the liquid and vapor phase? So again, we go to the x-axis, we find 0.8. Y-axis, 84. So this is 84. We try to check where they meet. It's a mixture. So what are the compositions of the liquid and vapor phases? So what do we do in this case? We draw a tie line, right? So let's draw a tie line. Straight line here. Then we go down. This will give me what? Vapor or liquid? So this will give me the vapor composition. And then this will give me my liquid. Alright, so then the liquid would be the X, the vapor would be the Y. I read it from the chart, it's around 0.73 for Y1, and then for X1 I said something like 0.85. I mean, again, it's an approximation. We don't have little ticks on there to know exactly what it is. Alright, so in this case, Y1 approximately 0.73. So y2 would be 1 minus that, so approximately 0.27. And then x1 approximately 0.85, x2 1 minus that. Looking at this figure, do you think we have more liquid or more vapor?
More liquid.
Why?
Because pressure
Right. So one way to analyze and know the compositions, right, of how much of each I have, is measuring the length of this line, right, and the distance to our dot that's there. So this length here. This length divided by the total length. So this small one divided by the total gives me what? The fraction in the vapor. This length here, the longer one, divided by the total, will give me the fraction in the liquid. And obviously, we have more liquid because we're closer to the bubble line in this case. All right, so just highlighting that. So therefore, mostly liquid because we are closer to this side. Okay? And this would be my bubble. And this is my dew. All right. Next problem. If the modified Raoult's law was used to fit the data, what would the value of the activity coefficient be for ethanol at Z1 equals to 0.3, T equals 70, and P equals to 90 kilopascals? So the first thing you want to do is write down what is modified Raoult's law. Okay, just to kind of think about what am I trying to find here. So we have YI equals XI, activity coefficient, multiplied by PI set. So I would want to know, I want to fit this to this data, right? And where do I want to fit it? At this given point. So the given point is 0.3, so this is 0.3. Temperature is 70, this whole thing is at 70. And pressure is 90 kilopascals. So the pressure is right here. So we can say we're somewhere on this line.
Is it x1?
Right here.
Because it's written z1. Is this the more fraction?
So here we have all liquid. Here we have all vapor. So in this case, I'm closer to the vapor side.
I'm asking about the more fraction, 0.3.
Yeah.
It's z1. Why?
It doesn't tell you what's the phase. So the problem is telling you this is the overall composition. Is it liquid? Is it vapor? I'm not specifying. You have to figure that out. By looking at the plot, you know that it's a Y. Why? Because it's on the dew line, right? So it's closer to the vapor side. So now we can say yi equals 0.3. So from this equation, now I know this is 0.3. First step. Pressure is given, I know this is 90, right? Kilopascals. What is PI sat?
It's 90 because it's on the line.
Yes.
So already the saturation line and next to pressure.
No, we're talking about in general. How do I find PI sat on this chart? This figure. The black line? Remember, the edges are the pure substances, right? So in this case, I'm looking at component 1. So P1 sat would be on the right side. So that's going to be approximately 72.5. That's what I wrote. So 72.5. That's that here. What's x1 in this case? In this case, where I have y1 is 0.3, pressure is y.
And y is equal to 0.3.
Yes.
Will line directly under 90. It's at 0.25.
Right, so going to here and going down gives me that value. Okay? So I approximated it as 0.24. So this here is 0.24. What do I do? Rearrange, solve for the activity coefficient. Because that's what I'm trying to fit. I'm trying to fit this equation to this system at this composition. So then, and therefore, gamma 1 is going to equal to 1.55. All right? So that's the answer for this question.
Doctor, what if is it line was between the both lines?
So then you would want to figure out, draw the tie line, go down. This is my y1, this is my x1. All right? Given the following data, prove that an isotrope in this mixture exists. So in the previous lecture, we talked about relative volatility. Right? Remember alpha 1, 2. So alpha 1, 2 equals to what? Remember, it was the fraction of the mole fractions for the first component divided by the second. So this is y1 divided by x1 divided by y2 divided by x2. You remember that? And then how did we prove that an isotrope exists? What did we do with this expression? Equals 1? Right. So if it equals 1, that's where the isotrope exists. But on here, we're missing that data, right? I don't know what y1, x1 is in there somewhere. So we need to show that an isotrope exists using this expression. What other thing did we do last lecture? This does equal, if this was modified Raoult's law, gamma 1 P1 sat divided by gamma 2 P2 sat. So that, we did do an example where we worked with the sats, right? But in this case, we don't have gamma, right? In that problem we had, what we did was we worked with the ratio, and then we found it using the expression ln gamma equals ax squared and so on. But there's a simpler approach here, right? So what we did in the last lecture is we looked at when the composition of one of them is close to 0 and when it's close to 1. What's the relative volatility? And then what we said is if it crosses the line 1, so if one of them is like 0.5, the other one is 3, then somewhere in between we have a 1. That means somewhere in between we have an isotrope. So that's basically what we do here. We check the limits. So check limits. And in this case, what we're going to do is take gamma 1, 2 at x1 approaching 0. So we take a point that's close to x1 equals 0 on this figure. So I picked, in this case, 0.1. Okay, so I picked this point here, this point, where we have y1 equals 0.1, and then x1 would be whatever the value from a straight line would be down here. Okay, so the point here I got, we wrote it as point x1 equals 0.05 and y1 equals 0.1. And then the other limit would be alpha 1, 2 at x1 approaches 1. I look at the plot. In this case, I took y1 equals to 0.9. So I took this point here. I drew a line across, went down, and took that point there. So that would be my x1 around 0.95. So in this case, x1 equals around 0.95, and y1 equals around 0.9. Okay? So in this case, I need more space here, so I need to add a page. All right, so now we're going to do the math using this expression here to find what's the values of alpha 1, 2 in these two limits by plugging in, right, what we see here. So at x1 approaching 0, we're going to have alpha 1, 2 equals to, again, y1 over x1 divided by y2 divided by x2. In this case, y1 is 0.1, x1 is 0.05. What's y2 in this case? 1 minus y1, so 0.9, right? Divided by x2, which is 1 minus x1, so 0.95, right? We get a value here of 2.11. At x1 approaches to 1, alpha 1, 2, again, same thing. Here we're going to use these values, right? So y1 is 0.9, divided by x1, 0.95, divided by 1 minus that, you see that it's the same as what we have up here, flipped. So this would be 1 over 2.11, and that is 0.47. So we can see here, we've crossed the 1, therefore an isotrope exists. Okay? We'll just say, therefore, crosses 1 somewhere between x1 equals 0 and 1, therefore an isotrope exists. Relative volatility. Okay? Alright, so now I'm going to add another page here. So we answered the question, we proved an isotrope exists. Okay, we're done with that. Just to kind of remind you from what we did last lecture, if you wanted to find what's the composition at the isotrope, then we use the relative volatility again, make it equal to 1, and then plug in values and try to figure out what's the composition there. Okay? So in this case, I'm just going to outline it for you. Okay? And then let me see here. So there's two more other problems, okay, that are related to what we already did. So if you want, you can practice these. Okay. Again, these require guessing and using these charts. So I'll write down what you should get as answers. Okay, and then you guys can try them out. So here for P3, you're gonna get, let's see the volume. The vapor, approximately 15.58. Liquid, 34.42. From that, you can get the rest. For problem 2, you're going to find the dew and bubble pressures. In this case, this is 59.38 psia, and pressure bubble is approximately 79.46. All right, and then the time is up, but let me just, for this problem, I'll just write down how to find the composition at the isotope. We already did it last class, okay, just to show you again how it looks like. So estimate composition at the isotope. So then what we do is we take alpha 1, 2 equals to alpha 1 P1 sat divided by alpha 2 P2 sat equals to 1. And then from there we say that gamma 1 over gamma 2 equals to P2 sat over P1 sat. And those in the problem were given. Okay, so this is P2 sat and this is P1 sat. So we know that this is, in this case, the ratio of 80 kilopascals over 72.5 kilopascals. Then we're going to take the expression that we showed last class, which is natural log gamma equals AX2 squared. In this case, we're going to assume A is constant. All right, so that means that A is not a function of anything, it's a constant value. We're going to solve for A, then we're going to use this expression for the two components, okay, to figure out what is X. Right, and then X will give me the composition at the isotope. So in that case, just to kind of quickly show you here, A is going to equal natural log of gamma divided by x2 squared. And in this case, what we could do is take a point that we already solved for gamma, 1.55, right? And take the x at that point and use it. So we have gamma, in this case this is 1, so natural log 1.55 divided by x2 would be 1 minus x1. So x1 in that case was 0.24, so then we just write 1 minus 0.24 squared. Again, this is 1 minus x1. You get the value of A to be 0.759. Okay? Then from there, we do the equation, natural log gamma 1 minus natural log gamma 2, which we showed last class. And then from there we get natural log gamma 1 divided by gamma 2, which is what we have up here, right? And that's going to equal, for a binary system, whoops. Should be up. I was trying to erase the lines that I drew there, but it didn't erase them for some reason. Okay. So this is going to equal, if you derive the expression, it's always going to be the same. Okay? So it's going to be, in this case, A 1 minus 2x1. If you remember last class, you asked me why is there a 2? Okay, same expression. And then you solve for x1, and then x1 is going to be 0.435. Okay? Now, if you remember, in the first question, I asked you what's the composition at the isotrope, right? What did we find it was? x1 equals 0.44. So doing this math and this assumption, we found it was 0.435. Pretty close to what it actually is. And in this case, we were only given these data points, right? So we didn't have all the data that's there. Close to true value. All right, so that's it for today.